Yeah, I signed some forms. Yep, I managed to go through the whole thing. There's one slide that's going to lag out, but I'll just try and hit it ahead of time.
Okay, it looks like we got most people in. So I'll go ahead and introduce Dan Gregory today. Dan received his bachelor's in chemistry and geological sciences from the University of British Columbia, and he did his PhD at the University of Tasmania in geochemistry. After that, with Ross Large. After that, he went on to do a postdoc at UC Riverside with Tim Lyons, and he is now a professor at the University of Toronto. As we're going to hear about today, his work is focused on geochemistry and microanalytical techniques, particularly of pyrite, to answer large-scale geologic questions, especially thinking about ocean and atmospheric geochemistry through deep time. He's also meeting with our group tomorrow. We've got a project going on using his fantastic, huge pyrite database, which I think he's going to tell us about, for predicting the formational environment of pyrite. So without further ado, thank you, Dan.
Thanks for that, Shauna, and thanks for everyone for coming to listen to a talk on fool's gold. So today I'm going to talk to you about my work with the mineral pyrite and the different ways that we can use pyrite, and it's basically going to be a sampling of my research for the last 5 years. So if you have any more in-depth questions, please ask me about it later. So one of the terms I'm going to throw around is framboidal pyrite. These are pyrite framboids, and they're a mass of microcrystalline pyrite that has been, was originally thought to have looked like a raspberry, hence the name framboid after frambois, which is French for raspberry. Over the course of the talk, I'm going to first go into some of the analytical techniques I use, which is largely laser ablation, but I've been branching into atom probe tomography and TEM more recently. And then I'll go and talk a little bit about how we've been using machine learning to try and understand in what environment pyrite formed based on its trace element content. And I'll touch just a little bit of what I've been collaborating with people at the Carnegie on using cluster analysis for that as well. And then we'll talk a little bit about the use of pyrite chemistry and understanding past ocean chemistry. And then I'll go back to economic geology and talk about it as a source for gold in gold deposits. So one of the main techniques I've used is laser ablation ICP-MS analysis. What we do is take our rock sample with our pyrites of interest, use reflected light microscopy to pick regions of interest, and then we use a laser to vaporize a small area of it in a helium atmosphere. That vapor is then transported with transport gases into the ICP, which tells us the trace elements that are in that volume that we've ablated. And we tend to use 3 different standards, one for lithophiles, one for chalcophiles and siderophiles, and one for sulfur to get our numbers. There's 2 different ways that you do laser ablation analysis, both spot and map version. The laser maps, you raster the laser over the area of interest, and it gives you a 2-dimensional map of the trace elements in the sample. Or a spot analysis where you hold the laser in one position and ablate into the sample. I tend to prefer using spot analyses because they're more easily quantified, and then that quantification is more easily compared with other laser ablation data, whereas maps, you can have ghosting of other elements as you ablate the sample over, and it's less systematic when you get it into a ppm value. This is an example of a laser ablation output chart, and you can see these are interpreted in a couple of ways. So the iron is this top one here, We have the ablation off period to collect background, turn the laser on, and we get counts. When it's relatively flat like this, it's generally been assumed that the trace elements are held within the structure of the pyrite, whereas if we get peaks like this, it's been interpreted that those are indicative of micro-inclusions within the pyrite. Now, this is useful in some regards, but we can't really tell with a 35 micron spot whether this is held within the structure, whether it's in evenly distributed nano-inclusions. So that raises the question, are the trace elements held within the structure of the pyrite, or are they in nano-inclusions? And the reason this is important is because there's been a number of different arguments in literature that invoke having some trace elements being substituting in the lattice enhance the uptake of other trace elements. Arsenic is the one that's been studied most. So the argument is that if arsenic 3+ is substituting for iron, the iron site in the pyrite, for every 2 arsenics, you have 1 void space just to balance the charge. So that would then enhance the uptake of larger cations like gold or lead. And then other arguments have been made that if arsenic substituting in the sulfur site, that enhances the uptake of cobalt and nickel and other more iron-like elements. But if they're not actually in the structure, then that kind of, we have to think differently about this. A little bit of a lag. So this is an example of kind of that, how we can look at for inclusions using laser maps as well. So these are just hotter colors is higher abundance of the trace elements. And you can see pretty clearly with zinc that there's a bunch of spots here and some that are quite high. And those are indicative of little sphalerite inclusions. And zinc is one of those elements that is most often quite clearly in an inclusion. But other elements here are a little bit harder to tell. So around the rim of this little pyrite nodule, we have, this would be about 50 microns from here to here. Yeah, sorry about that. So the first place we went to try and, we decided that we should go into finer scale to get an idea of how these trace elements are held. So the first place we went was to a pyrite lag deposit in upstate New York. The reason for this was it had been documented that there's a number of different varieties of pyrite in this one area. So in one sample, we would be able to check a bunch of different trace element abundances. And from the hand sample scale, we went down to a laser mount scale. We did a number of laser analyses on one side of a 1 centimeter diameter polished puck, and then looked at similar textures of interest on the other side of the puck because we didn't want to do more detailed analyses on top of the same area as the laser, because the laser would probably affect how the different elements are held, or might. So the next step was to do nanosims. So we did a series of nanosims maps on the areas of interest. And one of these areas was these large pyrite rhamboids here, where we could see that there was definite zoning of a number of the trace elements. And then in another area where we had smaller rhamboids, which would be more indicative of water column formation, we selected an area that had high selenium as well as other trace elements to do a lift out for atom probe tomography. And this is, so what you do for the sample prep is you dig a trench with a focus ion beam SEM on either side and lift out a very small kind of prism of pyrite and then carve it into a bunch of small tips that look like this. This is a TM image of one of these atom probe tips. And what we were aiming for is actually to get across the interface of 2 of these micro inclusions in the pyrite rhamboid. And you can just faintly see that there is kind of a difference between this side and this side, and we interpret that to be one of these pyrite rhamboid interfaces. So for those of you unfamiliar with atom probe tomography, you put your atom probe tip, and you have a local electrode that applies a potential across that, so it's being attracted, and then you use a laser to just kind of sputter off the atoms one by one, where they go to a position-sensitive time-of-flight mass spectrometer. And based on the time at which those atoms hit that position-sensitive detector and where they hit the detector, we're able to tell which atom it is and where in that tip it was. So we can do a 3D reconstruction of where the atoms were in that atom probe tip. So when we reconstruct this, we can see where the atoms are in that tip. This is manganese. And as you can see, they're pretty evenly distributed, which we interpret to be that manganese is held in the structure in this case. Now this goes against some papers that I wrote that said that manganese usually isn't in the structure of pyrite. And then the converse on that is where nickel and copper are much more concentrated on that intergrain boundary, which also goes against the paper I wrote where I argued that nickel and copper were usually in the structure of the pyrite. So we went from there and decided that we should look at some samples that had seen a little bit less geological activity. So we went to the Demerara Rise, which is Proto-Atlantic, so about Cretaceous age, but hasn't been like put on the continents and metamorphosed at all, as well as the Cariaco Basin, which is this one up here, which is off of Venezuela. It's a modern euxinic, so the water column is sulfidic area, and pyrite is precipitating from the water column being incorporated into the sediments. This is from the Demerara Rise, and while nickel and arsenic isn't too clear, you can see that copper is very much associated with these intergrain boundaries. This is a TEM liftout, and this tip is going across one of these boundaries between these individual microcrystals in the rhamboids. And we saw a similar thing again with the Cariaco Basin, where we didn't get across it, but we got the edge, which is elevated in both nickel and copper, and to a lesser extent arsenic. And it's so the diffraction pattern by TM is exactly the same. It looks like it's at the very least templating on that, rather than being a completely different crystal growth. Yeah. But that still is sort of an open question that we're hoping to answer with a bit more satisfactorily. Okay, so that's kind of the work that we've been doing to understand how the trace elements are held in the pyrite. But we'll go back to our laser ablation data. And one of the big questions was whether we can use pyrite chemistry to identify the source of a given pyrite unknown. So the reason for this was because in the past, when we spent more money on exploration for mineral deposits, we would find more mineral deposits. Kind of in the 80s, that decoupled, and we kept spending more money, but we weren't finding that many more deposits. So this is probably because most of the easy surface deposits had been found, and we've got to go deeper to find new deposits, which means increased drilling costs, which means we need to get as much information out of every drill hole as possible. This was funded by the South Australian government, and they had started a program of drilling deep drill holes under the cover in the Australian outback. So the question is, if you get a little bit of pyrite with a little bit of alteration, is that is that indicative of a mineral deposit? Should we drill another hole? Or is this just something that's unmineralized? So starting with that, the premise of that is that since pyrite is common in many different geological situations, it's probably something that's going to be in a lot of these somewhat progressive drill holes. And because the trace element content of the pyrite is influenced by the trace element content of the fluids as well as the precipitation mechanism, we should be able to and every ore deposit has a different fluid composition, we should be able to back out from the pyrite trace element chemistry what deposit it came from. So we selected samples from 81 different ore deposits and sedimentary formations, with sedimentary formations being our like background stand-in. And this was both new data and literature sources, and we tried to use this to define the trace element signature of pyrites from these different sources. I was at the University of Tasmania when this started, so down here, so we had a bit of an Australian bias to our data set, but we did try and get data from elsewhere in the world to try and make it relatively global in extent. And here I'm going to give a subset. We ended up with about 3,600 individual analyses. This is a subset just to make it a little bit easier to see the different patterns. And you can see as I start laying on a few of them, just using thallium and copper anyway, these are all grouping in very much a similar area. So it's not working super well now. But as we add some of our lower temperature sources like SEDEX deposits and sedimentary pyrite, the thallium is plotting in a different space, and a lot of the copper is a little bit different. And then VMS is relatively enriched in copper. And maybe you can imagine if you were looking at a whole bunch of different XY plots, you might be able to start pulling out patterns by drawing circles around different groups. But that wasn't and while it could be done, it wasn't very satisfactory because everybody in this room will draw different circles and sort of get different classifiers, and it's not very reproducible. It's also time consuming. So we decided to apply some machine learning technique called random forests. Now, random forest uses an ensemble of decision trees. So we use 500 different trees, and you feed it a training data set that defines the different possible classifications. And then each tree has different permutations of trace elements that it'll look out. And based on how it splits at each of these nodes, it will bin a given unknown and assign it a most likely classification. So if we look at these three trees, say if we go to copper first, it'll split our unknown into this group, and then we go to tellurium, it'll split it to this group, and then say antimony, it splits into this group. And for this tree, that would be classification A. We go to the next one, different permutation of trace elements. It gets put into a different bin, and that gives classification B. And then the next one has a different set of trace elements, different permutations. Again, it's classification B. So since the majority vote is B, that's the final classification. And you can also pull other data out of that in how many of those trees do pick one, and we'll get back to that a little bit later. And to walk through that with our data set, if we're just looking at thallium for that first tree, we could separate out 1 ppm thallium into this group, and then that's going to get most of our SEDEX, VMS, and sedimentary pyrite. And then if we looked at copper next and maybe made 100 the cutoff there, then we're going to, at the next tree, we'll get most of the rest of our VMS separated out. And as you add more trace elements, they're going to be separated out in a systematic fashion so we can identify our unknown. So we started with our almost 3,900 analyses. The first thing we did was split off a number of analyses from ore deposit types that we had a lot of data for. So it was all of the analyses from a set of given ore deposits. So the analyses from these deposits didn't influence the training data set or the classifier at all. The remaining analyses were split, where you had a subset of data split off from them, and those were used to train the classifier, and that's 120 from each deposit type. And we tried to get equal numbers from every deposit that we looked at. So if you use, if you have a given set of data points from one ore deposit that had a lot of data, if you add like just a random assortment, the one that has the more data points is going to bias your classifier. So we tried to keep it so each deposit gave the same number of analyses to the classifier. Once we had our training data set, we used that to train the classifier and then use the remaining data to test and refine the classifier. Then once we had our suite of elements for the classifier selected, we put back in the blind test data to see how well it worked, like in what would be a real unknown situation. So this is the initial test data results. So it worked pretty well. So the orogenic gold analyses were correctly identified about 79% of the time. So that's a B+, that's not too bad. And the best one was sedimentary pyrite that was correctly identified about 97% of the time. And this was pretty encouraging because that was our stand-in for unmineralized pyrite as well. So it's at least very effectively pulling off the non-mineralized varieties. And we found we could improve this by subclassifying a number of the data points as inconclusive. So remember I said that like just plus one more vote will give a classification. If we put in a requirement that you need at least 40% of the votes, and say if it's less than 40% of the votes for the favored classification, it's inconclusive, we're able to remove the data points that are less, we're less sure about. So that by doing this, we increase orogenic gold, which is still the lowest, to about 86% of the time, and sedimentary pyrites being correctly identified 98.5% of the time. So now that we have the classifier working, we put it back in our blind test data. So we didn't have as much data from IOCG deposits or porphyry deposits. So we weren't able to try blind test data on these ones. But for orogenic gold, sedimentary pyrite, VMS, and SEDEX, we did have additional data to put through. And this time our worst classification was from VMS deposits. And that was 84.6% of the time correctly identified. And sedimentary pyrite is still the most effectively identified at 96.7% of the time. But we had varying numbers of data points from the different deposits. So we thought we should go through and just check to see whether it was only identifying the deposits we had a lot of data for really well, or if it was doing pretty well with kind of across the board. So with this, we said if you had 65% of the analyses were correctly identified, that's a correct analysis. 35 to 65% correct was considered to be inconclusive, and less than 35% correct was wrong. And based on that criteria, they were all correctly identified except for one of the orogenic gold deposits. The next step was for this to work in an exploration setting. The problem with random forests is that it's always going to give you an answer, and that answer is going to be one of the deposit types that you told the classifier it was going to be. So we wanted to see how it would work in an exploration setting where you would have pyrites that don't really fit any of those classifications that we gave it. So is it going to be able to, it'll always give you an answer, but if we check at how conclusive that answer is, we can probably say that it's not, or we hope that we could say that it's not something that's in the classifier. So for this, we went back to one of my PhD chapter sites at the St. Ives Gold District in Western Australia. And this is a broadly an anticlinal structure and hosted in a greenstone belt with a few sedimentary interbeds. So here I identified 7 different types of pyrite, one of which is associated with a gold mineralization. So we have pyrite 1 and 2, which are sedimentary pyrite, both the fine-grained pyrite as well as nodular pyrite. We have pyrite 3 that occurs with pyrrhotite, kind of on the flanks of the deposit area in weakly mineralized veins. We have pyrite 4 and 5, that is like kind of this cleaner pyrite and this more sooty pyrite that occurs within this hashed area, which is an area of magnetite overprint that predates the gold mineralization. We have pyrite 6 that is associated with gold mineralization, then pyrite 7, which is just little bits of pyrite that occur within the greenstone host rocks. When we put this through the classifier, both the sedimentary pyrite and the orogenic gold were correctly identified. So we made this criteria to be a conclusive analysis. You need greater than 65% of the most common classification, and less than 50% of the analyses are inconclusive. So only 16 and 9% of the analyses were inconclusive, and they were 97.5% of the time was saying the sedimentary pyrite was sedimentary, and 84.9% of the time was saying that the orogenic gold was orogenic gold. So the next one, so those are get stars because they were right. The pyrite 3 and pyrite 7 were both only had relatively low most common classifications, so those were deemed inconclusive. And pyrite 5 had a large number of analyses that didn't meet the threshold of 40% conclusive analysis, 40% pick by the random forest to be a conclusive analysis. So that one was also eliminated. But it did highlight a mistake or an issue in that pyrite 4 was made it below our threshold of less than 50% analyses inconclusive, and was also 80% of the time calling it orogenic gold. So this is suggesting we do need more unmineralized pyrite in the classifier. But now I'm going to go on to talk more about that sedimentary pyrite and what we've been trying to do with it to understand past ocean chemistry. Yep. So a couple of reasons. Partially, we were mining data, and this is, so that is something that would be a part of it. So this is one tool that would hopefully fit into the petrology as well. But so that would be, this is to be used in conjunction with petrology. So yes, you would want to know if you didn't have any intrusive rocks and it came back as porphyry, that would be a pretty good indication that it's not working correctly. But we were aiming at using pyrite chemistry to get fluid chemistry. So that we were kind of stuck with using that as our tool. Yeah, fair enough. I know based on how I was able to do it and my colleagues, our success rate wasn't nearly this good. But yeah, that could have been part of the documented study. Any more questions? sorry, I wanted to touch on the cluster analysis that we've been doing with collaborators here. So these are just some pretty preliminary ones, and I think we'll be developing this more in the next couple of days. But one of the things that's come out of the cluster analysis that's really interesting is that using 3 clusters, it really pulled out the temperatures ranges of the pyrite that's formed really well, with most of the sedimentary pyrite being in one cluster, most of the SEDEX pyrite being in another cluster, and then more of the higher temperature hydrothermal pyrites being in the third cluster. And if we move on to look at more different clusters, we see a number of different sedimentary pyrites, while still the higher temperature ones tend to occur in the same cluster. So we're going to be talking in the next couple of days about what is this telling us about the different sedimentary pyrites and maybe the formation mechanism and like the sedimentary setting of these. So this is a reminder of where our different sedimentary pyrites are from. We were hoping to get them from as many parts of the world as possible. Again, we have an Australian bias. We also tried to hit formations to get as wide a range of different time periods as possible. This is still a work in progress, and what I'm showing you today is going to be a little bit less than what Ross has been continuing to put together at UTAS. But when we started to compare the trace elements in pyrite through time, we noticed that it matched actually pretty well a lot of whole rock black shale records. So this is Scott's molybdenum and euxinic black shale versus the molybdenum and sedimentary pyrite. And you can see we're relatively low in molybdenum in both in the Archean and the Proterozoic, and we see a strong increase as we enter the Phanerozoic. And similarly, if we look at the nickel-iron ratio in banded iron formations versus the nickel and sedimentary pyrite, we see a decrease out of the Archean into the Proterozoic and the Phanerozoic. And this broadly matches modeled molybdenum values in time, where the kind of average of the pyrite in the Archean steps up in the Proterozoic and steps up again in the Phanerozoic. And with cobalt, you see the converse, where the kind of average of the pyrite in the Archean drops into the Proterozoic and drops again a bit into the Phanerozoic, though our data is an awful lot more noisy than these model values. So this kind of suggested that on a very broad Earth timescale the trace elements in pyrite seem to be mimicking metal availability in the ocean, as shown by those whole rock methods. So we decided to check this at the section scale. So I got samples from the Wu-He formation, or the Wu-He section of the Doshan-To formation, which had been argued to record 3 different pulses of oxygen prior to the Neoproterozoic oxygenation events. And the way that these have been used traditionally is you use redox-sensitive trace elements like molybdenum, vanadium, rhenium, and uranium. These are used because they're mobile in oxidizing conditions and immobile in reducing conditions. So this means that if you have a large area of the ocean has a sulfidic water column, there's a high drawdown of these redox-sensitive trace elements. So that means that in areas where you have pyrite formation and black shales being deposited, because there's a high drawdown, it's going to be relatively low in these elements. Whereas if we increase oxygen and therefore decrease the footprint of sulfidic water column, there's going to be less drawdown. So the areas that are still sulfidic are going to be higher in these redox-sensitive trace elements. And for a modern day example, the Carriacou Basin has quite high molybdenum contents because most of the ocean is oxygenated, and this is an area where we're drawing down, where we have reducing water column and are drawing down molybdenum. So this is the work, the whole rock samples by Sahu et al. And you can see there's 3 periods where there's a strong enrichment in these redox-sensitive trace elements. And when we compare our pyrite analyses, this is molybdenum and pyrite, and this is a log plot, I'll note, but we have an increase in each of these intervals of molybdenum and pyrite. We see a similar thing with most of the chalcophile elements. So arsenic, not so much, but silver, antimony, selenium, all are increased in these intervals, as are cadmium, bismuth, and lead. And the reasoning for this is the chalcophile and siderophile elements kind of want to be incorporated in pyrite, so they're being drawn into the areas that you have sulfides forming. So like the whole rock, if you have a widespread pyrite formation, then you're going to be drawing these elements over a wider area, whereas if you have a smaller footprint of reducing water column, you're going to be drawing, kind of focusing those trace elements into those areas, so you're having increases in the trace elements of pyrite in the areas that you still have reducing conditions. And the reason why you use pyrite instead of just using the whole rock is because pyrite can be preserved up to mid-green schist facies, or the trace element content of pyrite can be preserved up to mid-green schist facies. So this will give us access to more basins to analyze for these sorts of paleo ocean chemistry studies, and especially in the Precambrian, being able to use somewhat metamorphosed basins would be beneficial because the whole rock methods are sort of reset by or can be reset by metamorphism. Right now we'll go on to, because I'm a kind of economic geologist by trade, I'm interested in the formation of gold deposits. And can this data be useful in helping us find new gold deposits? So if we look at just gold, and I'll talk about the Phanerozoic in a second, but you can see that there's a number of peaks of gold and sedimentary pyrite. And I should note that these are kind of the averages of many samples instead of just individual analyses. So these are, we feel are pretty real peaks. So what are the best source rocks for gold? So when we're looking for gold, for mineral deposits, we should be looking for not only where they're trapped and where they're forming, but actually what are they sourced from? So you need the source, you need the fluid pathway, and then the trap. And it's usually easier to find the source and the fluid pathways in the final site, because the final concentration site is relatively small in comparison. So the highest gold on average in rocks is in carbonaceous shales. Tholeiitic basalt tends to be quite high as well. But when we're talking about gold deposits, we're often talking more about arsenic deposits that has some gold associated with it. So for our source rocks, we should actually be looking for all those other elements that are associated with the gold. And when we look at arsenic, tholeiitic basalts don't have much arsenic, but black shales still do. So the model for sediment-hosted gold deposits is that you have gold enriched in early pyrite. During metamorphism or recrystallization of the pyrite or conversion to pyritite, the gold is freed from that early formed pyrite. It can travel with metamorphic fluids to favorable structural sites to form the deposit. And metamorphic modeling supports carbonaceous shales as being particularly good for this because, just quick, so this is like, these are measures of sulfate that is evolved during metamorphism and the pressure temperature conditions required for it. The top one here is for a system that's basically just a pyritic sandstone, but that contains no graphite. And the lower one is a system that contains graphite. And these lines are basically lines of pyrite destruction. So this is the amount of pyrite that's destroyed and free to give up its gold. And it's much higher at the same pressure temperature conditions in carbonaceous shales rather than pyritic sandstones. So this is indicating also that carbonaceous shales are more able to give up their gold, as well as in addition to having more gold to begin with. So this can help us find gold deposits because it would allow us to test basins as potential source rocks in a way analogous to oil and gas explorers, who will always go and look at the potential source rocks in the basin before they spend time or money doing seismic and drilling. And we can also look at kind of what's happened globally with the ocean chemistry and whether it's likely that those pyrites would be high in gold. So we noted that a number of different time periods, the sedimentary pyrite is elevated in gold, and these coincide with the host rock ages of a number of important gold fields in the world. So we have the host rocks of the West African gold deposits, the host rocks of the Yilgarn and Superior Cratons, as well as the Spottersrand deposit in South Africa, all coincide with these high gold and pyrite ages. And if we look at the Phanerozoic, we have a lot more data from the Phanerozoic, so it's possible that we would have kind of more highs and lows as well as in the Proterozoic and Archean, but just don't have the data yet. Or it might just because the Phanerozoic's a bit more dynamic. But we can see that we still have a number of distinct peaks, and they also correspond with the age of the host rocks, a lot of important gold fields, Carlin, as well as the Lachlan and Kazakhstani gold deposits, and the deposits in Victoria. So to check if this sort of worked, and one's a bit of a work in progress as well, we decided that we should go to a region that's not particularly well known for its gold endowment. Because if we show you that, oh, the Carlin host rocks are the same age, and we just go to Nevada, we're gonna get the answer we're looking for. But we went to Queensland because it's not somewhere particularly known for major gold deposits, but we as humans have mined gold everywhere. So let's see where the existing deposits were in an area that does have a few of these prospective host rocks, but not that many huge deposits. And so I colored the different units of the prospective host rocks through here, and then overlay the gold deposits, and they tend to match those prospective areas pretty well. I need to do the math to see exactly what the percentage is with those, or what the exact associations are with those underlying lithologies, but just at a first pass, it's promising. So with that, I'd just like to thank everyone for listening to me and ask if you have any questions.
The mic, so who has a question?
I'm just curious how you share your branching model with other people who might want to use it, since I don't do this kind of research.
Right now, I haven't unfortunately been able to publish all of the data due to some of the people who funded the research and a moratorium on that. If anybody has data, I'm happy to run it through the classifier and just see how well it's worked. I've done this with I'm in the process of doing this with a few people. And I've kind of given Bob and his group the data sets to work with the cluster analysis, like on a collaborative basis. So if people are interested, we can definitely work out collaborations. But right now, I was unable to publish it.
Can you make the classifier available without making all of the data available? I mean, is there any way to do that?
So I guess I could. I didn't really think about that.
I just wonder if you could make the scheme available without actually having to get the data.
You're probably
on
right. I didn't even think of
GitHub
that.
or a Jupyter Notebook or something.
Yeah.
Yeah. Yeah, okay. Sorry, another question?
Thanks, Dan. So when you're doing cluster analysis, of course, you're looking for as many attributes as you can for lots of samples. And you've been focusing, understandably, on trace elements. But as Connell mentioned, there's petrologic uh, attributes, there are morphological attributes, there are age can be an attribute. And I don't know if you've done any clustering using the age, sulfur isotopes, you go down the list. Have you thought more about if you had, in an ideal world, you had 10,000 pyrite samples, what additional attributes should you have in order to really um, discriminate between these different kinds of pyrite?
Yeah, so partially because we had to go to literature site sources as well, I wasn't able to put as much textural stuff in as I could. Random Forest isn't really great at bringing in that kind of metadata, which is part of the reason to collaborate with you guys. So we have a subset that has that data that would be really interesting to use, and I would like the community in general to put more textural data in than is currently done because it's really useful. It does have the issue that it is somewhat more subjective. And we tend to, when things like this are published, they tend to be published more as a sequence of formation, especially when we're talking mineral deposits, than a given texture. So it'll be like sort of within the paper that they describe the texture, but that's not readily, easily brought into a database like that. Sulfur isotopes would be great, but to get the sort of in situ data from sulfur isotopes, it's much more expensive because you have to go to SIMS with that. I'm working with a PhD student at UC Riverside. That's part of her project, is to bring some of that in. The early work on that is showing that it's super, super effective because, at more at getting the discrimination percentages even higher. But that's pretty early days. She's just got like metamorphic, hydrothermal, and sedimentary. But the hope there is to use it as a biosignature. At the back of the room, he's been waiting for a while.
Oh, okay, Steve, I'm coming.
The question I have is about resolution. You use the atom probe to look at high resolution about how cations are distributed in the pyrite. And of course, the most important one for your work is gold. And you probably hit more pyrite grains with a laser ablation system where you could pick up nuggets than anybody else because you're doing such a wide survey. What's your take on the distribution of nuggets of gold in the pyrite that you looked at?
So highly variable, I guess, is part of it. But I think it's going to come out that it's more and more common than we're thinking right now. So it kind of fits. If you're just looking at a laser ablation tab chart, sometimes they're in clear nano nuggets. Sometimes they're like really flat plans. But at least what we've done with the atom probe, it's showing that the arsenic isn't as evenly distributed as thought. And when people plot this sort of data, they use Martin Reich's plot there's a kind of a line on the arsenic gold plot. If it's above that line, it's a nugget. And if it's just like thermodynamically, if it's below that line, then it could be within the structure of the pyrite. But I think it's gone, in the literature, it's gone from being it could be in the structure to it is in the structure if it's below that line. And I think as we examine these further, a lot of those are actually probably like nano inclusions of gold within the pyrite. It's just that it has enough arsenic that theoretically it could be in the structure. Does that answer your question?
Since you're talking about pyrogenesis, how do you distinguish between ex-solution nuggets and nuggets that are formed separately from the fire? Because that becomes very important when you're talking about how things form, how it started, rather than how you find it now.
Yeah, so that's part of the reason why when I'm looking at how it's held in the pyrite, I'm looking right now just at sedimentary pyrite, so relatively low temperature. That's why we went to places like the Cariaco Basin, the Demerara Rise. So we can sort of get a handle on what at the earliest days it's looking like and how it's being incorporated. So then when we start giving some metamorphism to it, whether we're seeing similar things, whether we're getting more maybe exclusion textures due to like it exolving with a little bit of temperature and pressure.
I think Faye had a question.
So once you identify peaks and based on the averaging, and every those point has widespread data concentrations. So how you get information? Is there some information looking at the details on the peak and why? You know, I mean, it also could be a data bias and based on even some of the resolutions. So are you trying to figure out the high and the low? Or is there some systematics?
Yeah, so we try and get at that from going to multiple basins from the same times, and as long as we're getting high in multiple different areas at the same time, we can be reasonably confident that it's high in many areas. It is a problem, and we're always looking for more data. And there's also, we're also working, or I've got proposals, and I'm still looking for a PhD student, but actually to go on the edge of a well-understood basin and go through different sedimentary facies to see how much of a control there is on the facies. So it seems like there is a pretty strong control on how deep of water you're in, on how much different trace elements are being incorporated. So it was in one of the earlier versions of my papers and thesis, but it's hard to get a good idea of facies for a lot of these areas because it's not really there's not that many areas that have that great of control on the facies. So you'll read a paper and it'll say, well, it's deep. Okay, well, how deep is deep and stuff like that. So it's not well reported often in the sort of geochemical literature that we got our sample sets from.
I wonder if this classification has anything to do with the lead isotopes. I'm surprised that nobody was curious enough to look into see what kind of patterns maybe the Archean versus other things.
So we have that turned on for some of them. Because we went to literature sources, I wasn't able to bring different lead isotopes into my classifier because I would have had to give up basically half the data set if I was going to say, well, we need to look at all 3 lead isotopes.
But in terms of effort, the lead isotopes is a trivial problem. We have lots of lead, and in any
Yeah. No, I agree with you. People should report that.
Okay.
We have it in the data set collected at UTAS after a certain amount of time. We weren't doing it initially. We added it like 5 years ago now, but it's not, we don't have it for the whole data set, so we'd sacrifice probably half the data set if that was going to be used for this classifier. Yeah.
Yeah, so I think this and what Bob said and what Connell said earlier actually kind of gets at, what can we get out of an ideal data set? What is the ideal data set? So we can do some testing, especially with cluster analysis, where we can bring in these categorical variables like texture. We can actually start to look at these small subsets of data and say, oh, this is the type of information we can parse out of this. And then we can go to the community and say, hey, if you report lead, if you report this and that, we'll be able to do larger scale studies. So we hope that that's something that will come out of this collaboration. There's also something to be said for what is the minimum amount of information that we can still get something useful out of as well, which when we look at the data that's available out there, we can start to make some of those answers. So were there any other questions? Okay, if not, please join us for lunch. And let's thank our speaker again.